One of the more complex challenges in the FTC Decode season was figuring out how could you fit two robots inside of an 18-inch square base. In FTC Robots Revealed, we get up and close and take a look at all different mechanisms for how world-class teams end up building their robot. And we're here at the World Championships with Team 13532 Eaglebots.
Features 2 swerve modules rather than 4.
And they had one of the most unique ways that I saw teams try to approach the final challenge.
At the end of the match, the robot will tilt.
Now, there's a whole lot of whackload of different mechanisms that'd be able to make this thing click and work. They've got swerve drive, they've got different omnireal supports, they have a bunch of really slick ways of moving this artifact or the game element around the robot, as well as a collapsible hood that actually still stays pretty rigid using a worm drive.
That's fine. And then go up.
Tell me about your overall robot. What do we got looking at here?
Yeah, so our robot kind of centralizes around this wedge ramp-based design. And because of that, pretty much every other subsystem had to be designed around it. The ramp design works by, at the end of the match, the robot will tilt. This stilt will deploy down. Can you hold the mic? And so that really allows the robot to become this pretty concise ramp shape, which robot can then mount. We calculated this angle based off of common chassis designs, but what we saw was really prevalent were these really low to the ground chassis. And so we integrated this winch system where a robot will go on, these hinges flap down, and then they stop. And these are inspired by one-way speed bumps from Europe, where the robot comes on and then their wheel or chassis gets hot, allowing them to not leave our robot. This whole system runs on a belted gantry, where at the end of the match, it actually will pull up, allowing them to climb. However, you can see how that would interfere with our shooter conventionally. And so that shooter mechanism actually features a collapsible assembly, where at the end of the match, before we do endgame, the hood goes all the way down flush, and that shooter collapses using a worm gear drive, which we can see in this cutout.
Yeah, that probably makes a little more sense.
So our drive base also had to be modified to fit within kind of this unique profile. The first part of the robot we designed was this wedge shape, where it kind of features that 30-degree right angle, and every part of the robot has to fit within that profile. And so we were really only given about 5 inches for a fully omnidirectional drive base, which really isn't possible with a conventional mechanism chassis. And so this kind of gave a really practical reason to use coaxial swerve in FTC. And so our bot features 2 swerve modules rather than 4, which might be what we commonly see. And so those are going to independently move and drive in different directions. They have a custom TPU air wheel, which helps us really increase friction, which is a huge balancing act when using swerve, because you don't want too much friction where the wheel can't pivot, but you want enough where you're actually going to be able to effectively drive. The robot then has 4 dead wheels, which kind of teeters on that central driving wheel, ensuring that it's a stable chassis and these are able to move smoothly about the field.
And that's quite a narrow drive base as well. You have tipping issues with
so this
that?
rear wheel is actually not usually touching the ground. It's just between here and here. And so we had 18 versions of swerve, and a lot of the later versions were about moving this back and forth, trying to find where it would align perfectly with our robot's center of axis or center of mass. And so that was really designed in a way where it allowed that robot to put most of the weight on this drive wheel and not on the dead wheels, which are effectively just adding drag. And to do that, we also had about 5 pounds of custom lead plates that are in the swerve module.
Oh, that's
to
all the
help
way up here.
balance out the weight.
Okay. And how are you protecting that lead from getting damaged?
Those are CNC to shape, powder coated, and then a 3D printed TPU cover is put over it, allowing it to get hit repeatedly and not really deform. And then the powder coating is what's actually doing the sealing to make it FTC legal. The other part you got to see from the bottom is this belly fan feature. And that's the stilt right there. Get a little better view of that. This belly pan was added a little bit later in the season because we only have about 6 inches to fit the entire robot design in. In order to be able to have that 30-degree ramp, the entire robot had to be flat up to that 6-inch mark. And so fitting a 5-inch ball in that was a huge challenge while still having intake wheels. And so what we did is that belly pan allows us to still not drag the balls against the ground, but be just a few millimeters off of it in a way where in endgame, this can actually fold into the wedge. And so that gives us a little bit more adaptability and a lot more consistent intaking. The intake is also very unique in that it's a 2-stage intake. The first stage is going to focus on pulling the balls in, and it has a mix of...
rotate the robot down.
Like that.
Just down flat. It's easier to talk about the intake.
Yeah, so
in this respect,
this intake has a mix of Decode textured wheels and fingered wheels. The fingered wheels really function to get in and grab those holes in the balls, and they're at a lower distance. And so the goal of these is to go into the ball, the holes in the ball. And then the goal of the grip wheels is to, once we have kind of latched onto the ball, give it a lot more aggression when pulling it into the intake. In order to actually fit the whole intake system in, we had to drive it on a single motor, which we have a diagram of the powertrain we can show you in a minute. But what that meant is the first stage and the second stage had to be driven off of one motor. The second stage is geared across, chained in, and then beveled so that it changes the axis of rotation. This is kind of our indexing stage. Indexing, not sorting, which I think is a common misterminology. Indexing is simply pulling the ball into a consistent shooting position. And so that those 72 millimeter fingered gecko wheels will pull the ball to this stopper gate. Once that stopper gate is released, it'll move into our flywheel once it's in its actual shooting position. Right now, it's a collapse position. Hits that homing switch so that we know consistently where it's at during endgame. And so this controls our actual ball shooting.
So you've got a little, on the inside here, you have a hub here that's connected to a worm drive, and that's what this large
So
like connected to.
With that demo here, that shaft that we're actually driving on the hub is just simply this shaft here. Because of the height constraints, we couldn't directly drive the worm gear because it's just barely tall enough to fit a entire go build a motor in. And so that includes the swerve, where the motor is actually about 2 millimeters off the ground when we're driving, and the motor shaft ends at the top of this black plate.
Okay.
And so we had to find some creative solutions about how to actually do that. This tool that we're using is simply a way to be able to better manually move up and down the flywheel or move our wedge system back.
That is something that a lot of teams don't think of as maintenance holes, right? And putting in, like, you've got a clearance hole here so that you can actually get it and access this and manually move it up and down, because, of course, worm gears you can. Now, with your hood, it's interesting because rather than printing on a gear here, you've chosen a servoless on a sprocket, and then you have a chain that you have.
Yeah, so our hood is actually driven off of a chain, which is kind of forming a rack and pinion system. And GoBuilda came out with their bolt-on chain links recently, which would have made this a lot easier. But we found that it's a lot easier to give you kind of custom length rack and pinions rather than having to generate a really custom design. A really unique thing that I think some teams might be interested in implementing in a future season is our stilt is actually, let me pull out our set screw, driving off of a GoBuilda chain sprocket. And so that is directly bolted onto an Axon motor, which we can kind of see through that gap here. And so, are you able to see that? Okay, cool. And so that is actually not driving a conventional rack or a chain, but because of the pitch of GoBuilda chain, we're actually able to drive simply that 8 millimeter hole pattern. And so this is a custom steel variation of their rail, but
the 8 millimeter center to center fits well with the sprocket.
And so we've been using that for several years to do rack and pinions of custom lengths. And we actually find they're a lot more durable than a conventional rack and pinion because You're not limited
You're
to
compared
teeth.
to a 3D printed rack and pinion.
A 3D printed rack and pinion, or even their rack and pinion that they sell, because you're meshing metal with metal. You have a lot more aggressive bite on the teeth versus their 2mm pitch on all of their gears.
That's some really impressive packaging put together.
Yeah, the largest gap in anywhere in the robot is actually right here. It's about 1.5 inches by 2 inches by 2 inches. And so the largest empty space in the robot actually can't even fit a motor. We most recently added this back plate to give us a little bit more space. The entire season, like you might have seen in earlier iterations of the robot, was actually just running a control hub. We had maxed out all of the ports on that, including sensors, servos, and motors. And so in order to add this winch system, we ended up having to find kind of a creative solution for adding a second control hub. We designed this in such a way where after state, we modified this length here, so it doesn't take up so much of the actual box. It's kind of hard to see, but this inner rail is actually deeper than the outer rail. And so when we're in the box, we're taking up a smaller amount of space, which allows our partner's robot to overhang slightly. And so even an 18-inch robot design can free up these 2 inches on the back of the chassis for us to now control hub, an extra motor, number plates, and our custom Logitech camera.
And then you said, in terms of sensors in here, you're not doing any sort of color sorting, but you do have some limit switches on your flywheel, so you know when it's in the totally up, totally down situation, because that's probably one of the biggest challenges here, is make sure that everything is guaranteed back down in a flat position so that a robot doesn't
because we had issues previously in the season where they would run up, this wouldn't be down, and so they would ram that, and that would do two things. That could damage our flywheel, but then also this still is going very forcefully into the ground, and so when a robot hits our robot mounting us, it's putting all that force into bending that still. And so we actually had quite a few of these stilts bend in half before implementing that system. The hood has a custom limit switch kind of down in this channel that makes sure that we are able to consistently home the hood. Same as the shooter having one of those rev limit switches on a custom mount.
A limit switch, or is that a Hall effect sensor?
No, this is a limit switch.
The little touch sensor.
Yep.
Yeah.
And then this little bracket here actually holds our shooter into place. It's really hard, even with a worm gear, to get a stable shooter. If you've used worm gears, a lot of times they kind of work their way loose throughout a season. And so we end up with a lot of backlash. And so this allows us to drive it into kind of a frame holding that shooter into place.
And that's how you get it
when it's all the way down. And so that gives us really stable, consistent shooting, where we're actually only plus or minus about 1 inch on accuracy.
Okay. So you're saying there's not much. Oh, yeah. There's really not a lot of backlash on that comparatively. Yeah. Yeah. That really does help shore that up quite a bit.
And then we have a distance sensor so that we can increase our shooting rate, kind of tucked into the intake. We have multiple sensors in the swerve, including the built-in potentiometers and axon servos. We had to do a lot of work with wrapping encoder counts in order to make it so we could do multiple rotations with absolute positioning. And then we obviously have our camera system, which allows us to do auto aiming. We actually drive field centric, which allows the robot to function as a turret. And so one thing we determined at the beginning of the season was a turret really wasn't necessary unless you were getting pushed around, which swerve really helps to minimize. And so what we can actually do is aim while we kind of get into position. Unfortunately, at the beginning of the season, we were a little bit price locked and couldn't afford a Limelight until when they were already sold out. So we found that these Logitech webcams work quite well, and we actually have a 3D printed case that puts that into a much more effective form factor for us.
So what are you guys most proud of about this robot?
We gave ourselves the constraint that we had to complete Endgame because we knew it would be a bigger challenge. We gave ourselves a lot of packaging constraints. And so it's not just building a more complicated shooter for the fact of making a more complicated shooter. It's building a more complicated design that's actually adding functionality versus in previous seasons where we've had complicated systems that are very innovative, but really don't increase the functionality in a meaningful way. And I think that's something we're really proud of. and really, really proud of fitting everything into this packaging constraint where when we first started CADing it, we could not figure out how to fit this many motors, this many servos, and 3 balls into one robot purely based on volume. And so we were honestly really concerned about that and had to come up with some super creative solutions as far as where the actual motors are being placed, not just direct driving things or even simple belting.
Cool. Well, thanks so much for sharing, guys.
Yeah.